Okay, so any question from the previous two lectures? Okay, so our target is basically to calculate this invariant polynomial, right? And which we are promised to calculate using this group space integral and exponential of this character function, and which we define in terms of statistics. So what we did that for, let me close this, close kar diye. So for a connected compact group, we have learned how to calculate the characters for different kind of irreducible representations, right, in terms of the torus coordinates. So now for us, we know how to represent the character polynomial for some given representations for a given group, and then we have also learned how to calculate the Haar measure for that given group. And so this, for any given group, for any given representations, we know how to calculate this thing, right? But certainly this is the most simplified framework where we have only one symmetry or you have only one representations. So now what we'll do today, we'll try to find out that how to generalize this structure. Okay, so before that, we try to understand what are the basic principles of this statistics. Okay, so we have noted that this is a kind of a generating function which captures all possible tensor products of the representations. Okay, so at this moment, even before performing this group space integral or whatever, we are not claiming that this will contain only the invariants or so on. So it doesn't bother about the invariants. What it does actually, it takes the characters, okay, and take a polynomial in the characters and in the language of the representations. So you start from the lowest dimension fundamental representations and you do the tensor products and you capture all possible, the representations that that group can possess. Okay, so that is the thing, this generating function. That's why it's called the generating function, because it's generating all the representations, right? Now, if it generates all the representations, but we have to have the property of this statistics such that it can discriminate the boson to the fermion, right? So that's why it also captures the statistics. So how? So it is actually, you can define the statistics as, so this phi stands for boson, okay, and R is the representations. So for that, we write down equal to 1 to infinity phi r r chi r. Okay. So you can start even r equal to 0, but that because the trivial part. Okay. So now we can drop this r equal to 0, which is just an identity. But this is for the boson, and if psi is a fermion, okay, so for the fermion, because of this antisymmetry property, we will introduce as a plus 1 psi r by r chi r. Just on top of that, there is a minus 1 to the power r plus 1. Okay, so this captures basically the effect of your fermions. But this chi r here represent the fermion fields character, and here it is for the bosonic character. The way we have computed the character, and if you try to recall that structure, what you'll find out that if you think about only the internal symmetry, right? So internal symmetry is actually blind to the spin of those fields. For example, if I tell you there's a SE2 doublet fermion, okay, and there's a SE2 doublet scalar, okay, the components SU2 quantum number all are basically the same way, right? Because the discriminatory factor is coming from the space-time symmetry. So as long as we are not talking about the space-time symmetry, we are talking about only the internal symmetries, so it doesn't discriminate the spins. So that's actually help us to calculate the characters, because so far we have learned to calculate the characters for the internal symmetries. So now, if you have calculated the characters for, let's say, SU2 two-dimensional representations, okay, equally if the two-dimensional representation is Fermion or the scalar, the character function would be the same, at least the internal symmetry part. Where they will differ? They will differ, of course, when we will see how those fields transform under the space-time symmetry, and under the space-time symmetry, what are the characters for the Fermion and the boson. So that will be the additional factors. Okay, so one thing should be clear in your mind, that from the internal symmetry perspective, that this doesn't discriminate the spin, so you actually be blind to the spin, you identify the dimension of the representations, and you calculate the character function, and the character function will be equally applicable for, for a spinor or for scalars or so on. Is that point okay? Any question up to this part? No. Okay. So now, yeah. Mixed operator means? No, we are not talking about the operators as of now. We are talking about the individual representations characters, because operator we have not reached until we perform the integral. Okay. In the operator, they will be discriminated once you switch on the space-time symmetry. If you do not switch on the space-time symmetry, you do not discriminate them. So far we have discussed only the internal symmetry. So from internal symmetry doesn't discriminate your different kind of spins. That's the argument. So you don't need to calculate SU2 triplet scalars character and SU2 triplet Fermions character separately. You just rely on the representations, that's all. Okay, fine. So now this character satisfies this kind of additivity thing. Let us stop it. Higher prime equal to plethysticks of phi r chi r plus phi r prime. And this is quite simple because this is an exponential argument, okay? And because these are basically variables, there is no operator property so to say, and these are the complex number, so they just commute among themselves. So this property is basically as simple as that. Nothing new there. Okay. Now, let's say I have two groups. For example, in the standard model, I have a SU3 cross SU2 cross E1. Now just think about, you have a quark doublets, right? And those quark doublets can have quantum numbers under the SU2 as well as the SU3, right? So now you have only one field, but that field has two different quantum numbers, right? That means that field is transforming under the SU3 symmetry as well as the SU2 symmetry. So that's how I choose a representation phi, and which is written like this. What is the meaning of that? How do you read this part? That R1 is the representations under this group G1 and this R2 is under the G2. For example, if you write down, this quark doublet, you write down 3 and the 2. It's SU3 triplet, SU2 doublet, right? The same way. If this is the case where you have only one representations, but it transform under more than one symmetry groups, so its quantum number will be dedicated for each such group, right? So then you write down the statistics of this phi under these representations R1 and R2 as exponential r equal to 1 to infinity phi R1 comma R2 r chi R1 z say r chi R2 y k r by r. So you have written down the character of these representations under the group G1, and this is the character for these representations. And because these two groups that you are writing is a direct product, that means two groups are basically independent from each other, so that's why you can decompose their characters as a product of the characters for their individual group. Okay, so that's why we are actually exploring this SU2, SU3. Okay, they are two independent groups. We are not taking in semi-direct part of that thing. So that's why we can write down their characters as a product of these two characters. Yeah. Both for? Yes, so at this point when I'm talking about these properties, they equally hold for fermion and the boson everywhere. Okay, but when you write down explicitly the pathetistics, additionally -1 to the power r plus 1, only that factor. But all these properties of the pathetistics will hold for that thing. Okay. Yeah. Is that okay? Okay. So now we know how to write down this character now, right, for a multiple groups. But then there will be additional change in these definitions. Why? Because now this was a measure for particular one group, right? Now you have multiple group. So you are actually performing this group space integral for individual group space, right? For the SU2 and SU3 separately. And again, because they are independent, it doesn't matter to you whether you are performing this group space integral for SU2 group space or SU3 group space earlier or later. Okay, so we have to extend our hard measure, and in that case, we write down basically this polynomial as j equal to 1 to some n gj g mu j pathistic exponential of phi I rj. Okay, so you have now product of these hard measures for individual group, as many group you have in the context of standard model. So you will have a d mu with respect to SU3, SU2 and U1. Okay, and then the total, so you take each representations or any field you consider and then see how that field transform under this SU3, SU2, U1. You write down the character as a product of those three characters of three different groups, and that's the total character for that representation. You write down the pathetistics, and that's all. So in this way, the individual information that you have computed earlier, you can accumulate and dump in this definition of any arbitrary number of compact connected group and having any number of arbitrary symmetries. Representations. Okay. Any question up to this part? Okay, so I guess now what we can compute that for any given internal symmetries which are given in the form of connected compact group, okay, and whatever the representations we have, so we should be able to write down these pathetistics, the hard measure, and based on that, if you want to create the, and if you want to rely only on the internal symmetries and the invariant polynomials, you perform this integral. Okay, so which are basically reduced in terms of a complex integral. Just find the, write down a Mathematica, the simple poles. Okay, just the residue thing. That's all. So using this part, we should be able to calculate the composite operators. Okay, which actually invariant under the internal symmetries. So our task for the internal symmetry, now if you recall how we decompose the symmetry with the internal and space-time, internal symmetry is done. Nothing more than that. Okay, fine. So now, let's talk about the space-time symmetry. Now, before going into space-time symmetry, let me talk about that the polynomials that we are constructing. So these, as you have seen, that what are the variables we are choosing? Scalar field, fermion field, field tensor, and derivative, covariant derivative, right? And of course, if you are interested in a higher spin object, you can carry on this thing, but as I told you, we are interested for the SMIFT primarily, and which can be generalized to other things, so we restrict ourselves here. So these are all fine for the internal symmetries, but this guy doesn't transform under the internal symmetry. Okay, this is singlet under the internal symmetry, but this plays a very crucial role in this construction. Why? So there are two things are there. One is integration by parts. Okay. Now, what is the meaning? Why do we need this integration by parts? But because if you think how to define the action, you define the action as d4x Lagrangian density, right? So now, if there is some operator involve some kind of derivative, okay, because it's within the integral, you can perform this integration by parts, what we have learned in our basic calculus. Okay, and that tells you that if there are some two operators, okay, O1 and O2, which are related by this equation. What is this equation? That there are two operators O1 and O2 which are look primarily different, but if they are related by a total derivative term, okay, then I will either consider this or this operator. So O1 and O2, they are not independent. So in this polynomial, we may find out some structure in a same mass dimension, of course, okay, where we can find out that two or multiple operators are related to each other by this total derivative term. Now, why this total derivative term is not useful for us? Because here we are not interested in the operators which are lying in the boundary. So our quantum field theory construction, we are considering the manifold where there is no boundary. Okay, that's why this total derivative term will not affect any kind of physical phenomena. Okay, so integration by parts and this total derivative is connected to each other, and we will spend more time on this later. But this is the one way to understand this thing. But then there's another kind of constant, the quantum fields that we are talking about, they are dynamical in nature. Now, if you are dynamical in nature, you can find out their equation of motion, right? For example, so you can find out the equation for these fields, and then if you find out again something, these two operators are related to each other by the another operator, and the coefficient is nothing but the equation of motion of some dynamical fields under considerations. So this part actually drops out. So again, our conclusion would be either I will consider O1 operator or O2 operator. So just to remove the redundancy from my theory. So this is a naive way of looking into these two special constraint while constructing the operator basis from the group invariant polynomials. First, what the group invariant polynomials you computed, okay, they may have redundancy because of these two things. Okay, so we have to be careful that we remove the redundancy such that we can, the operators that we will be working with, they form a basis, and this basis I am using the same way that you know in the vector space. They are independent directions. So operators are, you can think like independent directions, so all are independent operators. Okay, yes. What do you want to see here? Yes, for example, you can think of this way, that you are doing this integral one by one, right? So you can think of, let's say there is a n-1, n number of integral you have to perform, or let's say maybe final, let's say 3 integrals you have to perform, right? So now you first perform this E1 invariance. Okay, now in the E1 invariance you get some structures. Those structures need not to be satisfying your SU2 invariance, okay, and SU3 invariance. So the thing is basically, you can think of this way, that all the operators have to satisfy or must be singlet under all the groups. For example, you cannot write down a standard model invariant operator which is invariant under SU3, SU2, but not E1. So this group space imposing a symmetry is like imposing a constraint. So that's why it is always reducing actually. In that way you can think of. Okay, does that answer your question? Not really. So we'll see. If you are working, for example, dimension 6 operator you want to look at, you look at the operator, no, equation of motion up to dimension 4. But if you look at for beyond that dimension, okay, so what are the dimension you will be working on? I would ask you to equation of motion previous dimension. So nth dimension, you find out the equation of motion up to n minus 1th. Yes, exactly. Yes. Any other question? Derivatives? There's a covariant, yeah. So vector field, I am not asking the vector field to come out. It is already in the inside, in the covariant formalism.
That's what that was my worry. How then O1 and O2 operators could be same. O1 and O2 might be having only scalars, but the third one is having vectors also.
Third one means?
Derivative.
No, in the covariant construction, okay. So this is the total derivative actually you consider, right? Yeah, so that is the total derivative will come out from that thing, because that is the covariant construction gives you actually. So in the covariant construction, you treat that as a normal derivative in the action wise actually, because you do not worry about the gauge fields, because then when you expand the operator, then only the gauge field interaction will come out. At this point, the gauge field transformation and all those things are blind because they are dumped there. So this D for all the representations are D. Okay. Yeah. Any other question? Okay. So now these are the basically tentative notion of the IBP and equation of motion. But what will be our target is that if you think that okay, so I get the invariant polynomial and I have to do it by hand manually and exclude those invariants, that's a very tedious and manual task and sometimes erroneous. So our target would be whether a symmetry guiding principle we can set up such that we plug that information here in this construction on top of this, okay, and then it will automatically filter out all those constants. So eventually we can claim the invariant polynomials that we are getting, they are independent, such that once we get them and then again manually we try to change it, check equation of motion, all those things that we don't want to do. So the way we construct the symmetry driven way to construct the invariant polynomial, we want to impose this equation of motion on IBP through a symmetry driven way. That is the target. Okay. So let's see how we can do that thing. Okay. But before that, we need to understand this IBP and equation of motion slightly more detailed way. So if you think of, for example, there's an operator O1, which is, let's say, del 4 phi r minus 1, and then another operator O2, del q phi del phi r minus 2. Okay, I can have these two operators. Now, one of the important aspects to understand the IBP is just count the number of derivatives. Okay, for shorthand notation, I am using the normal derivative, but in a real construction, we will transform them into covariant derivative. Okay. So look at how many derivatives are there. 4 and r number of fields are there, right? And here also you have 4 and also r number of fields are there. So then the primary lesson that you learned that IBP connects basically only those operators whose constituents are basically same. Okay, that means if I have some other operator, let's say phi and then some psi bar psi, okay, we should not expect that these operator will be related to this operator by integration by parts. Okay, so that's the primary lesson we learned. That that means that you have a D derivative operator and you have some fields. So now what I can do, I can make some kind of partitioning that where I should put those D's. Okay, so I can have D attached with every phi, okay, or I will attach 2D with one phi and another phi I will not attach any D. Okay, so they are giving different kind of structures. So when multiple operators having the same constituents, only there is a possibility, it's not guaranteed, there's a possibility that some of them may be related to each other by this IDT. So this important lesson, why? Because then you know exactly that which operators are related to each other. And then if you remember when I defined the operator class, what was the operator class? Operator class here is like a phi r del 4, right? So this is my operator class that, okay, I have an operator class r number of fields and 4 number of Ds. Within the same operator class, okay, I have a defined operators, right? Now, if those operators constituent are derivative, then within the operator class, okay, I can have multiple operators which are related to each other by the IDP. Okay, this is the notion of the IDP, clear? And when you should expect the relation among which kind of structures? Okay, okay. So for this kind of structures, you would expect the IPP, right? So now, let's say I have a phi r and del k with relation k less than equal to r. Why k less than equal to r? Because if the k is greater than r, then I can write down the whole thing as a total derivative. So, that will vanish. Okay. So now, if I have this kind of operator, what I can do, I can partition the k number of D field within this r number of phi field, and I can saturate up to this r term. The maximal what I can do actually saturation, that if my k equal to r, beyond that I can write down the total derivative kind of term. Okay. So this kind of partitioning I defined something by p k comma r. It tells you there's an operator where there's a k number of derivatives are there and r number of fields are there. So this is some variable I am defining. Okay. So now how to write down this variable? For example, if I have a phi 5 and del 4, which I can write down as a del 4 phi, phi 4, del q phi, del phi 4, del 2 phi, del 2 phi 4. Okay. So in this way, I can partition them. So I can see the all possible partitions are basically 4, 0, then 3, 1, and then 2, 2. So these are the independent partitions. Right. So if I do that, the lesson that I am learning, that for this p k comma r, okay, and then if I have another partition p k minus 1 comma r, so this can be connected by my IPP, because I am changing that one derivative from there, or you can think I am acting a derivative on this and I am generating this thing. So both cannot be independent. So now we can think of another example. Let's say I have a O1, which is del 4 phi, phi r minus 1, which is a partition 4 r minus 1. Okay, so thinking of, okay, how many these things are there. Okay, I'm just suppressing here 4 and r minus 1 to tag in this way, and then O2 as del q phi and phi r minus 1, which is p 3 comma r minus 1. Now you see here number of fields are same, but here extra derivatives is there, del 4 and here's a del cube. Okay, so now what we can do, this del of this p 3 r minus 1 is p 4 comma r minus 1 plus some other operators can be connected. So if we can find out this kind of chain rules or the relations, we should be able to count them and then find out, okay, which are the operators are related to each other. And from there, we can remove that thing. And if we do that for any given k comma r, this kind of thing, and allowed all the possible partition and add all those contribution for those construction, what you will find out some quantity, which let me define by q, which is written as k equal to 0 to d minus 1 to the power k dk. So box. What is the meaning of this? So minus 1 to the power k. Why? Because every time you take a partial derivative, you pick a minus sign from the integral rule, right? So that's why the minus 1 to the power k, okay? And d, how many derivatives are there, okay? And g is basically the representations under this spin group, SOD. I'll come to that thing, why this is important. And now what you do, you take the representations, okay, and then you take that wedge product. So this is the wedge product. It's nothing, that's a name, but you can think of it as an antisymmetric product. Okay, you calculate G cross G, okay, and take the antisymmetric component. Similarly, you take a K times, you take a antisymmetric product of that. Right? Like the Young diagram, you know, if you take two representations, when you take a product, you get the symmetric state and antisymmetric state, you take the antisymmetric one. So in this way, if you do that, okay, and if you can recast this structure in terms of some kind of a, character function or something like that, then what we can do, this counting will plug here, okay, as a scaling kind of thing, okay, and then it will filter out all my redundancy. So that's the idea. So we have to plug in this thing there, but at this way we cannot plug in there. Why? Because at the end of the day, what is this? This is some, integral over this unimodular torus coordinates. Right? So we need to learn that whatever the counting we are doing here, okay, we should be able to translate this in that language. Otherwise, I cannot perform the integration. I mean, in principle, I can write down mathematically plugging there, but I cannot really compute. So this is the definition, but this is not something which we can immediately use. So you have to translate that thing. Yes. Yeah. No, that's basically in your this term, na? Yeah. Where I have written down additional operator, something like that. Yeah. This is the OJ. No. So basically, that's the difference. You basically are independent operator. It's like a constant, right? So P3R minus 1 and P4R minus 1. Okay. If you calculate these two partition, you take the difference between these two partition, and that difference is basically your number of independent operators. But this, if you have a k number of D, you have to calculate for every shuffling of the k, right? Because you can perform k number of IBP kind of thing. You perform one IBP and you get a structure, you get next one, you basically add, and that's what we are doing here. So you start with kth number, you take the integration by parts of all the D, you exhaust the number of D, okay, and then you add all the contributions. And if you add all the contributions, what you get? Basically this one. Okay. So now this, so we'll see that actually EOM and then IBP, okay, they are at some point will be glued little bit. So far we are talking about only the shuffling of the D, and that's why the number of D and number of fields are basically same. Only those two kind of classes. Yes. Okay, so there's the two things. So once you do that, okay, so what you can do on top of doing this IVP, you get some kind of a structure. For example, like here I'm getting del 2 psi kind of structure, right? Now you can replace the del 2 psi by its equation of motion. You get a different configurations. So Exactly. So that's the next level of doing this thing. But at this moment, even it appears the del 2 phi, I'll keep it as a del 2 phi. Okay, I'll not replace this thing because IBP when I'm using, I'll not think about I have any kind of equation of motion. My thing is I'll start from this D, okay, and then I'll exhaust by taking a partial, integration kind of thing until I, exhaust the number of D's, this thing. And if you do every time, okay, you basically add all the configurations and that is the count you basically get. Yes, of course. Yes, of course. This is just a simple example because if I take more partition, it will have more convoluted structures. Like for example, 4 phi's, separately. Yeah. So 5, 4 and 5. Just to demonstrate what is the partitioning means. But yeah, you're absolutely correct. Because no guarantee that it will be like that one only.
Yeah, the partition functions too are in that case you will have.
Yeah, you have more actually. Depending on how many partition you are drawing actually. Yes. Yeah. Any further question? Okay, so here the partitioning, okay, so this P and this P is slightly different. Okay, thank you for drawing my attention. So here I am trying to draw your attention by how the D's are being partitioned. Okay, like here the 4, there's no D is acting here.
At one part there are how many derivatives?
Derivatives, yeah, exactly. There is no R here on, so to say. Okay, so this is like this derivative, so this is like a partitioning of different derivative positioning. So you have 4 derivatives. Okay, as he was also mentioning that if I remove, I can have a phi square, phi cube, then I will have a more comma. I mean the vector P will be more because then I have more options to place D in a different places.
So it will be 4 comma 0,
Exactly. But that's a choice actually. This is just to demonstrate a simplified one. Yes, but at this moment we are not doing that thing because we are talking about now the derivatives are singlet under the internal symmetries. Covariant derivatives. So that's what I'm saying. Though I am writing, this is you think of as a covariant derivative. Okay. So when I'm talking about the space-time symmetry, okay, this covariant derivative will transform only. Covariant derivative is a singlet under the internal symmetry. So that's why in the operator construction, if you see, okay, we write down as a phi 4 D2 operator. Even you have a 2 different Higgs, okay, still it's a D. Right? And while talking about, for example, if you think about how the integrating out was being done, the propagated expansion, right? So you can see the derivative appearing in the effective operator is originating from the derivative, from the kinetic time of the heavy field. Right? But do you care about that thing? No. Because at the end of the day, D, when you write down the operators, the inner structure of the D will be determined by on which field D is acting. That's all. Right? Any other question? Okay. So now, to understand this thing, what we have to do, we have to, make this count in terms of the space-time symmetry. Now, what is the space-time symmetry we talk about in 3+1 dimension? That we have already, Lorentz group and all those things are introduced, right? So you can think of like SL2C, or you can think of SO3,1. Okay, SO3,1 or SA1,3 is just the same, depending on how to define that thing. Okay, but what is the important part is basically it's not compact, right? And we know for the non-compact group, we do not have any finite dimensional representations for the unitary ones, right? But we are interested in the unitary representations. Okay, so that is one catch. That means immediately you can understand that the character computation that we have done, we cannot do it here. And second point, if you stick yourself up to this Lorentz group, what are the information you can extract from there? Spin and what are the Casimir for this thing? That's the concept things you exactly Pauli-Urbansky operator and p square, right? So basically, so that's why you define now. You have learned in quantum mechanics that basically we can tag a state by those quantum numbers, right? So there we can define the state by its angular momentum, okay, and the mass. But then what about the D, right? So this D requires a defined coordinates to be described. Okay, that's why we just working in a Lorentz group, we do not have the information about how the fields are scaled, okay, and how this covariant derivative and all those things are transforming. So that's why we have to extend that group, and that group has a mathematical name. It's called the conformal group. Okay. Now, the conformal group that we are interested in is basically, you can write down in terms of SOD, 2 or SOD plus 2, C, the complexified. Okay. So now, it is actually, we are considering the D equal to 2R in even dimension, because 3 plus, so D equal to here 3 plus 1, so D equal to 4. Okay. Because we are working in Euclidean now. So now, this R equal to, we write down in a D by 2, right? Okay, this symbol tells you basically whether D equal to 2R or 2R plus 1, the rank is basically R. Okay. So now, this representation I can think of in terms of R plus 1 dimensional torus. Okay. Now, when I am writing SOD plus 2, the reason is basically this R plus 1 dimensional torus, it will have some torus coordinates, right? So now, these R coordinates, which are basically I can write down as a x1 to xr, it is basically describing your SOD. Okay. And as an additional one, this coordinate which I define as a Q, it is basically your SO2 part. So I can think of this SOD, this group, as a which has a maximal subgroup in this particular form. Now here SOD is compact, right? For example, SO4, my Euclidean is SO4 is a compact, but this, when I'm writing in this particular form, but this is coming from the non-compact part. Okay, and for that reason, here all these coordinates were transformed like e to the power I theta I, where theta I belong to some real number. Okay, it is, so this part is basically very similar what we have learned for the SUN part. Remember Z equal to e to the power I theta I, and right, so these theta is a basically real number, right? So these are just my unimodular coordinate system. But for the non-compact part, this Q you can write down as a e to the power I theta Q, where theta Q belongs to a complex number. Okay, not only that, if you think about the compact and non-compact quantum numbers, okay, so have you ever realized that why spin is quantized? Because it corresponds to a compact group, okay, and non-compact group there is no boundary. So that's why the quantum number associated with the non-compact group are basically continuous. Okay. And what is the simple hand-waving argument to understand this thing? Just think about a free particle. Okay, you do not trap it. What is the spectrum? It's continuous spectrum, right? If you trap it, which is the boundary, the spectrum becomes quantized. So, compact group, we can impose the boundary conditions and we get the spectrum which is quantized, okay? But for the non-compact, it's basically continuous spectrum. And that's why the eigenvalue or the quantum number associated with this non-compact part will be basically continuous. Okay, and what is this non-compact part associated with this? This is nothing but called the dilatation. Okay, yes. This theta, yeah. Exactly, it's a scaling kind of thing, yes. Exactly, that's a scaling kind. Rotation, yes. Yeah. Exactly. Okay. So now, so then what we can do actually for SOD to what? Any state when I'm writing now, which I'm writing as a L vector, it says now how do I represent my state? By Dynkin level, or like the way I define the highest weight state and all those things, right? So there we can define some in this, and where all these L's are basically belong to half integer. These are basically my spins, and these are the SOD. If you think of it's a simply connected way, which is basically spin group. Okay, these are my eigenvalues are basically my spins. Okay. Now the other scaling dimension is coming from here, the quantum number delta. If I define, that is basically a real number, and that's why it's a continuous. Okay. So then, if I have to attach a state which is transforming under this symmetry, how do I define that thing? By this. So you have a L1 to LR corresponding to SOD part, and I have this scaling dimension. I define this way. Okay, so these are my quantum numbers to define the state. It's exactly the way you define the, in quantum mechanics, the angular momentum, depending on what are the, good quantum numbers you have. Okay. So then, this construction when I'm doing, as I told you, this group is basically non-compact, so I do not immediately can write down the unitary representations which are finite dimensional. Okay, so we have to find a way to do that thing. But before that, we have to understand why we do not have that. Okay. So in this group, we have these two generators, P mu, which is like a translation, and we have this K mu, which is the special conformal transformation. Now, K mu is nothing but you can think of like a P mu dagger. And if you think of what you have done in the angular momentum, a J plus and J minus, you start with a Jm state and you act J plus until that exhausted up to the highest weight state Jm, okay? And or if you start with any Jm, you act the lowering operator J minus until this J minus J. So there's a lower bound kind of thing. And why you have a bound there? Because you are working in a compact group, SU2. Right? But so now, action of P mu is basically like a lowering operator. Okay, so P mu translation serves as a lowering operator, and special conformal K mu acts as a rising operator. Now what is this P mu? If I do the inverse Fourier transformation, it's my del mu operator. So now let's say if I have a representations phi. Okay. Now when I'm writing this del mu phi, what I'm doing? I'm lowering that state. I'm again acting on del mu twice, thrice and so on. So I can continue doing this thing del mu 1, del mu 2 and so on. And because there is no lower boundary, so I can start from a state phi and I can create all this state by infinitely number of operation of del mu, right? And that's why this big, now if you define this state, what will be the dimension of the state? Infinite dimension. So this it has a special name. This is called the primary operator. Okay, so I'll start with the primary operator and then I am using my lowering operator, which is basically my del mu. Okay, by repeated action of the del mu, I am creating all these states and these are called the descendants. Okay, so then I can write down any representations R which is tagged with this delta and L. Let's try to understand this. I am calling a scaling dimension, and at this moment don't confuse yourself. The scaling dimension and the mass dimension are the same. It's not. Okay. Do not confuse the scaling dimension as the mass dimension. This is just an eigenvalue of that operator, relation operator, which is a continuous value. Okay. So these states are basically having a scaling dimension and then L are represented, and so this we can create. We start with some primary operator and then we can have del mu 1 OL, del mu 1, del mu 2 OL and so on. And this is in general infinite dimension. Now the question basically, again, we have to satisfy a criteria, or we have to find out a way such that we can extract only the unitary universal representation which are finite dimensional, right? So that means if the representation is unitary, this will put a constraints on delta and L. Okay, so once we demand that, that will put some kind of a constraints on delta and L. Okay. So here there are some bounds we define that for given L, okay, delta needs to satisfy a lower bound. Okay, and what is that? That is some bound, right? And this bound is called the unitary bound. Are not necessary all the representations will satisfy this bound. Okay, but what we are interested in, only those representations which satisfy this unitary bound. Why? Because if you see, if we have some unitary bounds, that means once we reach by this repeated action which saturates the unitary bound, okay, then what does it mean? We are hitting the bottom. Because once I act this del, I am actually increasing this scaling dimension. So primary operator is OL has some scaling dimension. Okay, so once I hit the bottom, I cannot hit it further. Okay, and then if I repeatedly act on that thing, I'll get null state. Or even if I repeatedly continue doing that thing, I'll get negative norm state. Okay, so we have to look for those state which has the scaling dimension of delta L. Because only for them, if I act delta operator repeatedly, I'll hit negative norm state or the null state. Okay. So we should look for only those. So how this unitary bound reads? The delta greater than delta L, and what is this value of the delta L? It's given as d minus 2 by 2 for L equal to, what is this? This is scalar. All the spins are basically 0. That's a scalar representation. Or you have a d minus 1 by 2 for L equal to half comma. What is this? For the fermions. And similarly, you can define this for other higher spin states. So you have this value for this delta L, which is the lower value of this quantity, okay, which is saturated, which is satisfied for this unitary state, okay, they satisfy for given L this. Now at d equal to 4, okay, yes. Okay, I am not using that language here. I'll talk to you later. Yeah. Okay. Yeah. Okay. So now for d equal to 4, what is this quantity? 1. That is the at 4th dimension. That is the mass dimension of the scalar. Right. For d equal to 4, what is this? Delta L is 3 by 2, and that is the mass dimension of the fermion fields. Right. So now you can see already this value of the delta L is what needs to be satisfied is basically the mass dimension. So we have to find out those states, okay, for which delta L is there, and we can satisfy these unitary bounds. Okay. Up to this part, any question? Okay. So now, when a bound is satisfied, that is delta equal to delta L, so for some operator, then if I act del on that operator, okay, I'll get first null state and then the negative norm states. Okay. So we need to remove null and negative norm states. Okay. Now what is the meaning of that? A realistic example. Okay. If I have a free scalar theory, why I'm talking the free theory? Because for the free theory, the scaling dimension, okay, and the mass dimension, they matches. Right? And now for the free scalar theory, what is the equation of motion? Del to phi equal to 0. Right? Now I hope now you started getting the glimpse of that. So means if you start with the phi, okay, and you create different kind of operators by acting derivative on that thing, automatically del to phi is 0. Okay, right? That means from the phi and its structure, you have to remove the del to phi from that. Okay. Similarly, for the fermion, del psi equal to 0. Okay. So then, what you will do for the fermion field when you talk about, you act del on that. Okay. And those state what you will be constructing, you have to remove from the primary state. Right. Similarly, for your field tensor, what is your del mu f mu nu? Is J nu current, right? If the del mu J mu is what? 0, right? So if you define any operator in terms of J mu, I have to remove the del mu J mu state from there. If I have a f mu nu, that means del mu J mu, that time I have to remove. Okay. So what is the bottom line? That you start with some primary operators and then you remove those states from there, and this removal procedure in this language is actually shortening the tower. So if a tower of state, we are removing them. We are shortening the tower, right? That's why these are called the short representations in this conformal language. Okay. So then our target is basically how to calculate these short representations. So if I can, now what is this short representation you should expect? That there will be this kind of tower, okay, where there is no boundary or something like that, and by length, what should be the name of this? Long representations, right? Now in the long representations, when I impose this kind of unitarity condition, which are eventually satisfying my equation of motion, okay, that will remove those negative norm state and null state. So I'll create a short state. So short states are basically written in terms of long states minus some other operators. Okay, so that's why the short representations will see how to write down the long representations minus some structures. I'll take 1 minute. Is that okay? Okay. So now, what will be the generic structure for that? For example, let's say you have operators phi, del mu1 phi, del mu2 phi, del mu1, del mu2 phi, and so on. You have a list of these operators, right? So from this set, what I have to remove? Del 2 phi, del mu1, del 2 phi, del mu1, del mu2, del 2 phi, and so on. So this part I have to remove. Now what is the meaning of this? You think that the del mu1, del mu2, del mu3. Okay? Now among those three indices, I contract two indices. Right? So if I contract two indices, I get del mu1, del 2 phi. Right? And because equation of motion I have maximum power is del 2. So if I just contract two indices out of this and remove them, okay, I should get my short representations. Eventually, what we'll do, that we need this basically to find out this. Okay, tilde stands for the short representation. When I am putting a tilde, that implies a short representation. No tilde is a long representation. So this means basically it's just the chi d. Let me write down and then I'll explain what is that. So these short representations is my long representations when n is less than 2. That's obvious because you have no contraction thing. So then there is nothing to remove. Right? So then my short and long representation are same. But if n is greater than equal to 2, I start pairing two dels and get a del square. Right? So then I have these long representations. What I have done basically, I have taken any representations, okay, and then I take a nth copy of that and symmetrize that, construct the representations. That's how I create a representations minus the n minus 2, because out of that the 2 are basically contracted. Okay, so that gives me the constant. So this I'll remove. Okay, so in this way I can construct this thing. Okay. So I think, yeah. Okay. So this is the basic rule of shortening the representations. Okay. But now, next class, what we will do, how to write down these states, which are basically long representations I'm talking about. Okay. And then different kind of spins, spin 0, spin half, spin 1, how these shortening things I can do explicitly, I'll show. And then I'll explicitly calculate the characters of the representations and plugging into that Hilbert series definition. Okay, and that will take care about my space-time symmetry along with the IBP and equation of motion. Okay, and once we do that, then whatever the structures we will be getting will be forming a basis. There will be no redundancy. Okay, yeah. Any question? Once we start unitary bound, we have only for those states I can have the shortening rule. So when the delta equal to delta L, then I have to remove those things. If the delta is greater than delta L for those states, I don't care. Yes, shortening rule. Because those are the unitary representations. Primary operator, you can start with the primary operator with that. Yeah. For example, F mu nu, which is del mu nu minus del mu m, right? So if you, but you consider F mu nu as your quantum field itself. So you have to declare then that way. For example, if you are constructing an operator in terms of current, then del mu F mu nu is J mu, but you are considering J mu as your operator primary. You start from there then. Yeah. P mu dagger, yeah. In this construction, because we need to feel the problem is really it's unbounded from below, right? For non-compact. Yeah. That's why we start with an operator. Yeah, exactly. Exactly. If you want to know what is the primary of that, yeah, exactly. Then it will be needed. Yeah, that's true. Yeah, this is slightly different language, I can understand, but we'll do some explicit examples and that will be clear. But I guess, I hope that it is clear that why this IVP and equation of motion can be recast through this symmetry rather than explicitly imposing them in terms of fields. Now you can see the structure is beautiful in a sense. You don't need to, take care about the indices of the fields and all those things, and for different theories, different fields are there. But if you have a mathematical prescription, then just for the representations point of view, you can embody that part. And you don't need to worry about for defined model in a different way. So there is no manual implication of equation of motion or IVP. Okay, that I have not done yet. Yeah, I have not done it. Because once I do the full series, then I'll attach a kind of a scaling with each fields. At this point I didn't, because then the scaling with the delta they may confuse. But once I define them in unitary, then the delta L I fixed for them, then I can use a universal mass dimension for them. But yes, absolutely, I'll come to that. Otherwise, you cannot truncate that Hilbert series. Yes, absolutely, absolutely. That delta L. Delta.
Yeah.
Yeah, delta for for any, no, that's what I'm saying, that for any operator, the unitary bound for this free theory is basically the mass dimension. And those operators are of our concern actually. So we need to start with those primary operators who satisfy the delta because that's the unitary bound. And for given L, for the spin, we can write down this for all the arbitrary spin particle, L equal to 1, L equal to 2, and so on. There's a way to write down that thing. Yes, delta L is defined, because that depends on the L, na? Oh, delta, that you have to define by acting those K and, yeah, that's from the conformal symmetry you can calculate actually.
Okay.
Yes.
Given a operator,
Yes, you can calculate this delta, yes. But here, okay, sorry, I was thinking that, okay, delta L, yeah. Because we are interested in those operators which saturates the unitary bound, which is the delta L. And delta L is defined based on the L, small l, spins. It was slightly loud. Yeah, I will see that thing. Because, how do that thing? Because here, if you can ensure only the group invariants can project out. So Lorentz symmetry in the Lorentz space when we perform the integration, that will give me the Lorentz invariant scalar, because that's the right? So for example, when you perform the SU3, d mu SU3 when you are using that integral, what you are ensuring that all are basically color singlet. Similarly, when I perform the integral in the measure of the Lorentz symmetry, that will ensure which are Lorentz scalar. SOD part, yes. The measure when you define. But yes, the hard measure for the SOD we have not defined yet. Yes, you have to, yeah. But anyway, I'm around, so yeah, they can ask later also.